Faraday's Law. Here are your priming questions, and there will be additional questions at the end for AC versus DC that we're going to be using to help jumpstart our discussion in class. We are going to be starting a new lab in class. This is the Gauss Rifle Lab. This is a pretty fun lab, and you're going to set it up as I've shown you here. So this would be a ruler, and these would be steel spheres, and these would be your cube magnets. Now what you're going to do is you're going to set these up like this. So you're going to have one cube and two spheres. And you're going to have a separate sphere off to the side, and this other sphere you're going to bring close enough, and then it's going to hit this magnet. Now, you're going to make some observations and draw some conclusions from there, and then you're going to add another one in line like this, so that whatever happens from here will interact with this setup over here. Now, these are relatively small pieces, so you want to be careful with all of the materials. Please retrieve any pieces that are dropped. Also, I have limited number of supplies, so please do not take too much for yourselves. Also, I had some issues last year with some students taking the magnets and the spheres, so please leave everything in class. So, electromagnets. Electromagnets are current-carrying coils of wire with many loops. They produce a field similar to a bar magnet's field. So this is what it would look like if we were to coil up some wire, have a current going through it. Now, we already know that there's a link between electricity and magnetism, so current produce electromagnetic fields, and so the magnetic field that's produced by this coil is reminiscent of a bar magnet. So we could actually overlay a bar magnet here if we wanted to, and the magnetic field would be the same or very similar. Now what we have to be careful here is we use conventional current for this, which, remember, goes from positive to negative, even though we know that the electrons are what move. And so I found this funny comic from XKCD, and you can see the link there. Read through that, and we'll move on. This brings us to the second right-hand rule. So using conventional current, your fingers represent the direction of the conventional current, and your thumb represents the north pole of the magnetic field. And so you can see that with this coil, it goes around like this, and so you would have your right hand looking like this, so that would represent the current, and then your thumb represents the north pole, and so the field as it's produced looks like this, as if it were from a bar magnet. Now, there are three primary ways to increase the strength of an electromagnet. The first two you could have actually figured out from the virtual lab, so that's to increase the number of coils, increase the current / the voltage. The reason why this is really the same is we can't manipulate one without manipulating the other, because the resistance is going to be the same for our coil. And you can think back to Ohm's law for that. The third one is going to be new for you. It's to add a ferromagnetic core. And now I want to introduce the idea of permittivity to you. Permittivity you can think of as the concept of a dielectric. And so this goes back to the concept of capacitors and how to strengthen a capacitor or to increase the capacity of a capacitor. And remember, with the dielectric was a insulator in that case, but it had special properties in that it could align to the field inside of the capacitor. In the same way, we can think of our iron core as having all of these little domains, and iron by itself is not going to be producing a magnetic field, but when it is exposed to a strong magnetic field, like that of an electromagnet here, these domains can all line up in the same direction. And so when that happens, the magnetic field is causing the iron to produce its own magnetic field, because the iron is now going to be like a magnet. It's a temporary magnet, so since it's producing a magnetic field, it will strengthen the magnetic field as it goes from this electromagnet. So this is how we increase the strength of an electromagnet. It's the concept of permittivity, the ability of these iron domains, in this case, to be able to align to the magnetic field and to be able to produce its own magnetic field. So there are many different applications. The first is the simplest detector that we have for current, which is called a galvanometer. This is the grandfather of our multimeter, grandfather of our ammeters and of our voltmeter. Our voltmeter and ammeter are all different designs of a galvanometer. And so this was the original way of being able to detect a current. And some of these can be very, very sensitive, measuring down to microamps or even smaller amperage than that. The other applications are going to be motors and generators, and these are what convert between electrical and mechanical energy. We have actually already built these simple motors, and this is a more complicated motor, a much more in-depth design. It can be used for industrial applications, things like that. So this is a modern day motor, and this is the simple motor that we designed in class. All right, which brings us to Faraday's law. Faraday's law is sort of at the core of a lot of these ideas. The induced voltage is proportional to the product of the number of coils and the rate at which the magnetic field changes within those loops. And what is important here is the magnetic field changes. If the magnetic field doesn't change, it cannot induce a voltage, and that's important to note. And so this is where we need to talk a little bit about AC versus DC, which we'll get to in just a little bit and much more in depth in class. So Faraday's law deals with the magnetic field change within those loops. Think of this as the opposite of an electromagnet. Rather than putting a current through the coil to produce a magnetic field, we have a magnetic field that's moving in the coils to produce a current. It's just the opposite of what we've been talking about. And so for class, what I want you to be thinking about is going back to the virtual lab. What did you figure out about AC versus DC from the virtual lab? There's a lot that you could have drawn from the virtual lab. What is the difference in the magnetic fields in particular? And also, there was a transformer section. Which of these can be used appropriately for transformers? And now I want you to think about why. And also, what exactly do you think transformers do? If you've forgotten a lot of this, go back to the virtual lab. It's still on the Marist website. And you can go back through the transformer in particular and see what are the differences specifically between AC and DC.